The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, good morning. So, in today's presentation, what I'm going to talk about is basically what are the strategies that we can implement to enhance resiliency as well as fire resistance of modern concrete structures. So let me say what modern concrete structures is. I will explain to you why it is important. Conventional concrete, both from the material as well as the type of buildings we have, structural systems we have significantly changed over the last few years. Though concrete is excellent in terms of fire resistance, we may not draw the same conclusion with some of the new constructions in terms of materials, structural shapes, as well as the buildings we have. So for this, definitely we can adopt new strategies to enhance the fire resistance. That's what I'm going to show in this presentation. So first, explain why fire is a significant hazard for built environment. Talk about what are the problems with the modern construction, basically, modern buildings. Then I'm going to present a little bit of, to show you what factors significant influence based on a lot of experimental as well as numerical studies, especially relating to new types of concrete. Then I'm going to present some strategies that can be adopted. Concrete is one of the widely used materials which are used in building construction as well as in infrastructure. And one of the main advantages of concrete, though we don't, in fact, a lot of people don't even know about this, it is fire resistance properties is a significant benefit of using concrete. That's how it came into existence as well. Now, there has been significant research and development activities over the last 3 or 4 decades, especially with concrete technology. And if you pay closer attention, today we are making concretes as strong as steel. In our lab, recently we tested ultra high performance concrete beams. This is one of the projects with Air Force we have, US Air Force, which are 240 megapascals. Okay, so this is us, and when I was a student, not too long ago, right? I used to study for concretes which are 20 megapascals. So look at the way we have evolved. Though I think we are not using 240 megapascals in the field, we are using 90, 100 is becoming common, even in precast industry and stuff. Okay? So, fire is a major requirement when you use in buildings. A lot of people don't realize this because a lot of this is in the background documents or whatever, in the appendices and stuff like that. In fact, that's the governing factor for a lot of designs. Now, the emerging trend, what's happening over the last few years based on man-made threats such as terrorism and stuff, are basically based on a lot of, to prevent, enhance the resistance. Resiliency is becoming a key design parameter in a lot of critical infrastructure, okay? Concrete structures typically exhibit high level of resiliency, no problem there, especially under events such as, impact loading, blast, etc. However, when it comes to fire hazard, resiliency is not talked about or is not looked at in the design scenarios. Now, this statistics you saw in the first presentation, both Steve's, I think they went through how fire came into as a design issue. And if you look at the data, there were more than 1.4 million fires in the US in 2015. Many of them were residential fires, single family homes, but there was significant number of high-rise fires as well as the data indicated. Now, so it can cause thousands of dollars and billions of dollars of damage around the world. Earthquake is a problem in the west coast of US. Hurricanes is a problem in the Midwest, right? In the west coast you have seismic, in the east coast you may have, or the south you may have hurricanes, in the Midwest you have tornadoes, for example. But fire, from small communities to big communities, everywhere fire is a hazard which has to be considered in design, right? Now fire can happen, as it was shown, after most earthquakes you have fires, including recent earthquakes in New Zealand and Chile. There were post-earthquake fires. A truck hits a bridge, huge fire starts. Impact doesn't do much, but the fire does more damage than the impact itself. 9/11, the towers would have been standing today if there were no significant fires, right? The towers collapsed not because of the impact, it collapsed because of the fire, right? So fire is a significant hazard for the built environment. It's impossible to prevent all fires. So there are a lot of systems put in place: sprinklers, heat detectors, smoke detectors, exit paths. Then comes the last one, is structural fire safety. The building has to stand up for sufficient length of time so that firefighters have enough time to fight the fire, or the fire itself, it cannot go on, it will itself burn out. So for this to happen, you need to have structural members, you have sufficient resistance, which is basically the fire resistance or the structural fire safety. And all the time sprinklers don't expect it to work, as the statistics have been shown. Right? So this is very important for the safe evacuation of the people, to provide safe environment for the firefighters to fight the fire, as well as to minimize the property damage, to bring back into occupancy quickly. This is very important, and to control the spread of fire from one compartment to another compartment. Keeping the fire small is the most important thing in fire design. If the fire is small, it's piece of cake for firefighters. If it spreads to the whole floor, you are in big danger. If it spreads to the 2 or 3 levels, then it's most likely to collapse. That's what is showing either in World Trade Center buildings, recently in California near San Francisco, whatever, the building which collapsed, or in Tehran recently. So anywhere you see, more it grows, worse it is. So to keep that small, that fire small, compartmentation is the key, and that's what the fire resistance is mostly about. Now, higher the fire resistance, higher the resiliency. Now, just quickly, there was a fire in this building. This is a concrete building in Delft University of Architecture. I was involved as part of investigation this fire with 2 other people from US. So in this building, a coffee kettle, electric short circuit, huge fire starts, 14-story building, a significant massive building, built in 60s. Now it continued to burn. The fire, first I think they thought it's just the water leak, because there was a small mini explosion because of the short circuit around the coffee kettle. Pipes broke, water went down. Then I think it took certain while. There was a lot of wood in this building. Though it was a concrete building, all the farm work, first of all, architectural studios, there was huge amount of wood, as well as all the farm work was left itself. So the fire started to burn. Huge amounts of fire. It spread to 2-3 stories. For 50 firefighters would have died if they had not evacuated in time, or if they had not come out in time. So, okay, the insurance payout was 100 million euros on this one. So the building collapsed. Okay. So resiliency. This was not designed for fire-induced progressive collapse, which was an issue. Now, typically what we do in conventional construction, as I said, it has significantly high fire resistance, so never a problem. All we need to do in these buildings is basically to look at, provide sufficient cover thickness. If there is a concrete member, all we want to make sure that the reinforcement, the temperatures doesn't reach about 500 to 550 degrees centigrade or 1000 degree Fahrenheit. As long as you do this, typically no problem. This is what we used to do, okay? Because of the good fire resistance of conventional concretes. The second thing what matters in this one is the thickness of the concrete member or the cross section. You have to have minimum dimensions so that you have enough mass. Now, so in fact, ACI 216 currently says these are the requirements for 1 hour, 1.5 hours, 2 hours, 3 hours, 4 hours if you want to get fire resistance in the columns. these, if you have 8-inch column, which is the cross section of 8 inches, minimum dimensions, you can get easily 1 hour. If it is 10 inches, you can get 2 hours. This is as simple as that, okay? Now, this used to be very good. Basically, more mass you have, because concrete strengths used to be 40, 30, 20 megapascals. High reserve capacity you have. Typically, we never used to use all these nonlinear methods and stuff to optimize it in yesteryears. Now, higher fire resistance, higher resiliency. Now, what are we looking at? Modern buildings typically are much, much taller than what used to be before. And our cross sections are becoming smaller and smaller because we adopt all this nonlinear analysis, advanced techniques, and all this, as you all know. Now, not only that, from the fire point of view, typically today's buildings are much worse in terms of the fire load, I call it. Too much furniture, everything, whatever, we accumulate too much junk, whether it's in our closets, whether it's in our shoes, 10 pairs of shoes, 12 pairs of shoes. Before, traditionally we used to have 1 pair of shoes. My son has about 20 pairs, walking in the gym, he needs 4 pairs. 1 to the basketball court, and from basketball court to walk to his locker room, and locker room to come out, and then the snowshoes. It's unbelievable, the civilization is changing. And this is very bad from the point of view of fire. I know it's bad from a lot of other societal these things, okay? And this is very bad. And our compartmentation is changed. Before, we used to have nice compartments. We go to older European traditions, buildings. Today's buildings, everything needs to be open. My wife, she wants to cook and she wants to watch the TV at the same time. She wants to watch the kids. Everything, you leave it open. It's very bad for fire. Very bad from the fire safety point of view. So compartmentation. So today's buildings, my message here is very bad, both in terms of fire loads as well as ventilation characteristics, which can go out of control easily. So current provisions may not be directly applicable. We need to make innovative measures. Look at from structural side. It's not just the building heights and changing. We used to use nice solid slabs. We used to have nice solid beams. Look at today's cross sections. Everywhere we are making holes. To send something, because this is where we are going. Look at this deck slab. We were reducing. And typically lower mass. Because of this, you have lower thermal mass, lower fire resistance, or lower reserve capacity, lower fire resistance. It's not good. This is what is happening. Now, what else is happening? The third problem we have is these higher strength materials. Any newer materials have lower fire resistance than the conventional materials, whether it's wood, concrete, or steel. Why is it? As you can see, these concretes are made taking into consideration, we get higher strength, higher stiffness, they're all good. Typically, they have lower water cement ratio. That's where you get the higher strength. And you add a lot of fines, silica fume, fly ash, all these things you throw in, right? Now, typically, as we used to know, concrete in my undergraduate days used to be made of cement, some stone, some sand, and some water. Today, we add so many chemicals, just like we take vitamins every day. Right? So concrete, you throw in a lot of these admixtures, early age cement, you can get any property. Anything you want. You want early age strength or later age strength. You want, fine workability. When you add all these things, the characteristics change, especially at higher temperatures. Now, let me explain to you how. So this concrete is a conventional concrete. This is the loss with temperature, strength loss, 100%. See how it drops around 800 degrees centigrade. But look at the higher strength concretes or modern concretes. Can you see that there? Even at 150 degrees centigrade, there is a significant drop. This is not good. The second much more problem is the so-called spalling which can happen in concrete. What happens? This is a conventional concrete column. We tested in Canada, hundreds of columns, these ones. One of the projects was with Portland Cement Association. Look at the high strength concrete column. What is happening? This concrete has, as I said, cement it has permeability of about 10 to the power of minus 16. It's a conventional normal strength concrete, 40 megapascals, 110 megapascals. When you reduce the water cement ratio significantly and put all these fines, the permeability reduces, which is good from the durability point of view. So everyone is happy with that. But on the other hand, When these columns are exposed to fire, this permeability reduces to the order of about 100 to 1,000 times, anywhere, somewhere that, it's very hard to get these permeability values. When you have this column exposed to fire, this column exposed to fire, this is the new concrete, water becomes vapor. That vapor cannot easily comes out here because you have a much higher permeability, the pores. But here, that permeability cannot, very small, so that water vapor cannot come out. So the pressure starts to build up inside the cross section. When you increase the compressive strength from 40 to 110, but the tensile strength goes up by 2.5 to 4 megapascals. Not much. So when the pore pressure exceeds the tensile strength of concrete, boom, boom, boom. So this is called fire-induced spalling. Okay? It is much more a problem in higher strength concrete. This was seen in Eurotunnel, in a lot of practical application or practical real life fires, as well as a lot of tunnel fires. This is very common issue, as well as especially when the fire scenarios are very high intense, this happens. We have done a lot of work as well as other groups to establish the problems with this newer type of concrete and strategies. We carried out experimental, numerical studies. Number of PhD students graduated in our group, as well as around the world, number of studies have been done, and some guidelines have developed. I will quickly go into this. I don't have time to go into all the studies, but let me present something quickly to show you how the strength of concrete or modern concretes have lower fire resistance as opposed to traditional concretes. Lot of these parameters influence the fire resistance, not one or two. They are interdependent, very complex. Now look at this. This is a conventional concrete, normal strength concrete. Nothing happens till 6 hours. Take it for granted. Real tests which were done on full scale columns at National Research Council of Canada. But for higher strength concretes, can we expect the same thing? No. It reduces. Right? Up to 3 hours, maybe you are lucky if you get it sometimes. Okay? Then look at the confinement. Conventional concrete, you can have ties like this. This is the conventional way of providing ties. But if it is done same thing for higher strength concrete, this is for normal strength concrete, higher strength concrete, look at this, what happens. Even within 90 minutes, this 110 megapascals column, the ties open up because of the pressure which is generated. I told you about the spalling. This is what is left after 90 minutes. But if you bend these ties at 135 degrees, wonders. This will last for 3 hours, the same column from 90 to 180 minutes. Okay? Now, let's look at that. Now, I don't have much time. The problem is in concrete structures or steel structures, you all know eccentricity is a significant problem, eccentric loading. So this is, in fire, we don't even consider this in today's design, biaxial bending or uniaxial bending. Perfectly you have a column which is loaded uniaxially. But after 15 minutes or 20 minutes into fire, if it is 4-side exposure, no problem. If it is 3-side exposure or a 2-side exposure or a 1-side exposure, what happens? One side is losing the strength quickly, but the other side has significant strength. So your center of gravity doesn't coincide with this. So you are going to get either uniaxial or biaxial bending. You all know, I don't have to explain to you, under biaxial bending is a significant, this is not considered, it is much more a problem with newer constructions and newer high strength concrete, especially because you are using a very small cross section, small mass, okay? So this is 2-side exposure versus, as you can see, 3-side exposure versus 2-side exposure. We always think 4-side exposure is the worst, right? Look at this. This is the 4-side exposure versus 2 adjacent side exposure. Okay? This is not even codes and standards doesn't properly account for this. And typically in a building you can see this. This is a 4-side exposure. But if there is a wall next to it, if the column is built into the wall, you might have 2-side exposure or a 1-side exposure. Okay? Okay, this is what happens. This is the 4-side exposure, as you can see. This is the axial deformation on this column as a function of time. And this is what happens, as you can see, with 2-side exposure. So 4-side exposure, a lot of people think is the worst case scenario. More sides I have fire is maybe the worst. Need not be. Okay? Now, fire severity is a significant thing. Today's fires, as I mentioned to you, are much more like this. It's, we design under ASTM E119 fires, today's fires, a lot of times, can be very rapidly growing if there is a fire in a parking garage, in a structure, because you have hydrocarbon effects. Even all these combustibles are much worse than cellulose fires. So much damage is done when the fire goes up, and then sure, it cools down. But the fire resistance of, under some fires may not fail, but under some fires, design fires, it may be much worse than standard fires. Now, look at one of the things to overcome this is using fibers. As you can see this is a concrete column, high strength concrete column. Spalling happening in spite of using those ties. But if you add polypropylene fibers, you all know these fibers are you don't need too much, about 0.1% by mass. You throw in these fibers. What happens is, when the fire happens, the polypropylene fibers melt at about 160 degrees centigrade inside. They are discontinuous, they are spread out throughout. When they melt, it creates the channels of the pores. And through those pores, your pore pressure gets alleviated, no spalling. So this can continue for a long time. And look at this, even after 3 or 4 hours, very little spalling. And you can add steel fibers as well. They are beneficial as well. If you want to use it, that's a different story for a different application. But adding fibers can significantly enhance the fire resistance. Now, okay, these are same thing, I am repeating it, so let's skip this. You can use hybrid fibers, especially in tunnel structures. What are the strategies you can adopt? So, first and foremost, you can modify the time configuration to get significant increase in fire resistance. So, concrete is typically good, but newer concretes have some problems. To overcome this, one of the main strategies, this is what Portland Cement Association, we did a lot of work and developed this, together with Canadian Cement Association as well as Cement Association of Canada and Portland Cement Association. Adding more lateral confinement significantly enhances the fire resistance, just like in the case of the seismic design. Okay? So it obviously enhances the resiliency. Look at this, then you can make small modifications in terms of, I missed one point, adding fibers obviously. As I mentioned to you, either polypropylene fibers or steel fibers, or a combination of them in different applications. We have tailored this for different applications. Then look at this, you can make modifications either in mixed design. Typically limestone aggregate will give you some extra fire resistance, right? Lower the load, higher the fire resistance. You can add protective layers. That's the European code approach. I don't know how much it is beneficial from the cost effectiveness and stuff like that, but the other ones are much more effective. Just to mention to you, based on our research, this is all incorporated in our ACI 216.1, the latest edition which came out just last year. So ACI 216.1 has these provisions. Now, the other most important thing, this is an advancement which is happening, is to carry out rational advanced calculation methods, both from the fire resistance point of view and resiliency point of view, okay? This is not typically done in concrete buildings today, but if you want to establish and show that concrete structures have good fire resistance and taking realistic conditions into account, you have to do at a system level analysis by accounting for the different fire scenarios that can, tailoring fire scenarios, load levels, restraint conditions, and actual material properties, as well as the failure limit states. You can establish this. The procedures are there, and I don't think we have much time, okay? So you can generally model this for a specific structure or a structural element, both at the elemental level or at the system level, to enhance fire resistance. You can come out with some strategies. Now, basically in the conclusions, all I want to say is resiliency under fire conditions should be considered in design, especially for critical structures. It's very important. There are a number of problems with respect to newer types of construction, especially with newer types of concretes as well. So, however, you can develop proper solutions as shown here, either through tie configuration, modifying the tie configuration, or fiber reinforcement, okay? You can develop through proper experiments and numerical methods such as performance-based designs, okay? But still, there is number of research areas which is missing, especially related to, for example, spalling. How to predict spalling, when spalling occurs, where exactly occurs. The predictive models are still not there. So I think that's where the research should be going. Thank you very much. Yeah.
Yeah, so I think I heard you right at the end, I'm gonna ask it again. So from the standpoint of spalling, we still don't have a good handle on that. Is that a fair statement?
Very good statement. People are working on it, but it's very hard. I think because the problem is at higher temperatures, the instrumentation is a significant. Even today, we have advanced so much, we can measure only temperatures at higher temperatures. Strains, we cannot measure. Deflections, indirectly, we can measure. It's a big problem. And same thing, spalling pore pressure. I think there is no methods at all. So I think there is no handle on that.